Hello and greetings again from Stuart at Berkshire Guitar Amplifier Repairs. For the history hounds amongst you, it's currently late January 2021 and we're in the middle of our second large COVID-19 lockdown here in England. So that's why I'm cranking out so many videos, that's why you see me in the same old clothes. What's the point of changing my clothes or shaving or doing anything really? May as well just let myself go. Today we've got quite an interesting project. I wouldn't normally make a video about this, but I thought it might interest you if you're interested in the subject of guitar amplifier bias. On the bench we have a Carvin 100 watt legacy amp, which a viewer Paul has brought into me. He's made it himself, which immediately started alarm bells ringing in my mind. It can be a complete can of worms when somebody has made their own amplifier. But I think you'll be fairly impressed when I show you this amplifier and show you the quality of Paul's workmanship. The problem he says he has with this amp is that no matter how he adjusts the bias, the tubes get too hot and indeed start to red plate eventually. Well, that tells me it's got to be a problem with the bias. It's a bit of a no-brainer, so it's just a question really of finding out where Paul's gone wrong, if he has gone wrong, and why the bias isn't right on this amp. So let's crack straight on. I'll show you the amp top and bottom and you can have a look and see what Paul's done. So here we are, top side of the amp, and as you would imagine it's very clean. I mean, it's brand new, he's only recently built it. He's built several amplifiers, so this gives me a bit of confidence that he knows what he's doing. So not a lot to see top side there. I've taken the power tubes out because obviously they were getting hot, and any tests that I do I'm going to start doing immediately without any tubes in. Some of them are showing signs of having heated, like this one here. You can see that brown, see if I can get it over here, see a bit better. You can see that brown ring around the valve there. It shows it's been overheating. I'm hoping to be able to save the tubes. I'll put them on the tester at some point once we fix this and see if we can save him the cost of a new set of tubes. So there we go, we'll flip it over underside and I'll show you what he's done on the underside of the amp. And here we are, bottom side of the amp, and as soon as I saw this I was immediately filled with confidence that Paul knows what he's doing. This is pretty well made actually. Great soldering, nice layout of components. This is not what I expected to see. I expected to see a horror show which would involve me in many hours of corrections and diagnosis and things like that. Not my favourite pastime, but this is good. He's built a couple of amps already. He obviously knows what he's doing, so it's either a silly mistake or something else. So immediately what I'm going to be looking at is this area of the circuit here, which is the bias part of the circuit. There's the diode which is doing the rectification, there's the capacitor that's doing the smoothing, and here's a little trim pot which allows you to adjust the bias. Now of course Paul's turned that down to absolute minimum and he's still getting a problem. So the next thing I want to do is to confirm Paul's diagnosis by popping in a couple of tubes. I'll put in the outside pair and I'll put them both on bias meters, and let's have a look to see what's happening here. Alright, I've put a pair of tubes in the outside positions and I've brought them back out to the bias meters here. This is one of the advantages of having two bias meters, because you can monitor what's going on in both tubes at the same time without having to swap and change, and they're not terribly expensive. I don't know, $100 or something like that each from Euro Tubes. They've got a new model out now which is better than this, but I haven't seen it, so if you buy one you might get the new model. So we're switched on, we have the red light, standby's off, so I'm going to turn on the standby, or the HT, and then we should hopefully see the bias current start to climb, and I'm getting ready obviously to turn the HT off if it starts to get a bit crazy out there. So here we go, HT on. So we have 438 plate volts and 100 milliamps. Look, 92 on one, way too high. Turn that off immediately. Right, so what I'm now obviously going to do is to just stick my meter onto pin 5 of each of the output valves and see if we have a negative bias voltage. He may have missed off the connection to those, and those grids could all be floating, which would certainly account for that excessive current. I find it hard to believe he's done that, since he's done such a good job on the rest of the amp, but you know, who knows, it's easy to make a mistake, particularly when you're close to a project. So I will put the camera on the overhead and get set up to quickly measure those grids. We're going to have to be fairly quick because we don't want 100 milliamps going through these tubes. Back in a moment. I thought I'd quickly show you my natty homemade overhead boom. It's just a piece of very rigid box section alloy, G-clamped to my shelf, which is at a perfect height. You can't see too well, but it kind of comes around here, up here, and bends back on itself, and the camera attaches here. That's because, of course, I want the camera facing down here, not the other way around. Otherwise everything would be upside down. And I'm sure you can guess what this marvellous contraption is here. Yep, you've guessed it. This is exactly at head height, and I caught my head a few times on the angled aluminium, enough to make me wrap a bit of foam around it. So there you go. I'm just going to attach the camera onto here now and have it pointing down like this onto the chassis. Right, here we are all set up on the overhead boom. I thought I don't need to get too clever and measure the bias on every grid. I'm just going to measure it on one of the valves. I think what I'll first of all do though is just check what the, you know, if we have any bias voltage on this capacitor here, which is the bias smoothing capacitor. So I'd expect to see, I don't know, 50 volts negative on there or something of that order. And if we don't have any bias voltage there, of course, then we are in trouble. So let's have a look. The amp's on. I don't need the HT on for this, so I'm just going to leave that off. And let's have a little dab around here. I've got one probe connected to the chassis, the other probe here. Okay, we've got a negative bias voltage there. It's minus 31. A bit low. I'd expect to see a little bit more than that, but let's just have a little look on one of the tubes. So here's the tube here, pin 1, 2, 3, 4, 5. It's this pin here. 5 is the grid. I'm going to go on there. Oh, and so basically the full bias voltage is being applied to this grid. He's got the pot wound to maximum bias, minimum bias current, maximum bias voltage. So we have, well, since we're here, let's just have a little dab around. There's another grid there, minus 30, that's okay. I haven't got the HT on, by the way, so the valves aren't cooking. There's another grid there, minus 30, and the final grid there, minus 30. So we are getting negative bias voltage to all 4 output tubes. And the plate voltage, I'll just turn this up to 750, not for long. Where are we? There we go. 440 volts on the plate. Okay, so what am I thinking? We have the negative bias voltage. I don't feel 30 volts is enough. We're maxed out here on the pot, and I'd expect, I'll go and do some calculations in a minute, but I would expect, I don't know, minus 35 or minus 36, which, and that means I'd expect about minus 50 or something here, which is being adjusted down to minus 35, minus 36 here to give you a bit of adjustment range. But we're only getting 35 volts here. Sorry, we're only getting 35 volts on the negative, on the smoothing capacitor. So I think I'm going to have a look at the schematic and see how this bias is derived, because it's not high enough. There aren't enough volts there to correctly bias these tubes. So I'll be back in a minute when I've done some research. Hi there, I'm back again. I've been about an hour actually going away and doing some research, so let me report back to you. First of all, my intuition was correct, and that minus 30 volts is nothing like enough to bias those EL34s. It needs minus 36, minus 37 at that plate voltage. That's why the tubes are red plating. There's nothing wrong with the construction. There just isn't enough negative bias voltage. So then I thought, well, okay, you know, most bias circuits are fairly simple. You just take a winding off the transformer and rectify it via a diode and smooth it. So what's gone wrong here? Then I found and started to look at the schematic, and the way they have generated the bias voltage here is very peculiar. I certainly haven't seen it before. You may have seen it. I had to stitch the schematic together from two separate photographs, so it's a little bit of a mess, but follow me through on this. I think you'll find it interesting. So here is the bias part of the circuit. Here's the bias pot, and the negative bias voltage gets smoothed by this capacitor. By the way, note that capacitor is upside down, look, as you'd expect it to be. The positive goes to ground and the negative goes here to smooth, because we're dealing with a negative voltage. Okay, well, here's our diode, which is doing the rectification of the AC to produce our negative bias voltage. So I'd expect to see some AC coming in here, and that normally comes from a separate tapping on the mains transformer, which is called the bias tap, or even a separate winding sometimes, to give you 50 volts or something here, which you can then rectify to produce the DC. So I started following this back, expecting it to go to the mains transformer. By the way, here is the mains transformer. It's drawn rather unusually as a block. And I started following this back, and I came across this capacitor. I thought, what on earth is that doing there? C45, 47 nanofarads, quite a small capacitor, at 630 volts. And this now does indeed go off to the unusually 350 volts AC. This is the HT winding of the transformer. 350 0350, standard HT configuration. Indeed, these are the HT diodes. This circuit goes off over here. I didn't bother to attach it. These are the HT diodes which will get rectified, smoothed to produce our HT. So they are taking they're taking a sniff of the 350 volts AC. Now normally we'd have to somehow get that down to 50, which would involve huge power resistors and stuff, but the way they've done it is to put it through a very low value capacitor, which won't pass very much at 50 Hertz, because it's a small capacitor, but obviously passes just enough to produce an AC voltage on here of about, I don't know, with this load resistor of about 50 volts or something. That's a flipping weird way of getting the bias, but that's what they've done. So now what I want to do now is to measure, I'm going to measure on the scope the voltage coming in here. I expect it to be, 350 volts or something AC coming in here. Then I'm going to have a look to see what's coming in here AC, and we'd expect it to be a lot lower, of course, than 350. And I think that's not going to be big enough to produce our to get rectified to produce our negative bias. And spoiler alert, I've immediately seen that if I increase the value of this capacitor here to allow a bit more of this AC through at the frequencies we're interested in, 50 Hertz, we can up this AC component here and hence fix our bias. So that's my plan. I'll show you a couple of measurements, and then if it's as I think it is, I'm going to dab another capacitor across here. I don't know what this is 47 nanofarads maybe. I'll try, I might try 0.1, 100 nanofarads, and see what that does. And then I can adjust on test. So rejoin me when I connect the oscilloscope to these points here. Right, here we are ready to do some measurements. On the schematic, this is the capacitor that is of interest to us. On this side, we're expecting to see a high AC voltage, which is loaded down by this 100k resistor to provide a lower AC voltage there, about 50 volts peak to peak, which is then rectified to produce our DC. So let's have a little look to see what we've got on here. over on the actual circuit itself, this is the capacitor. Here's the high voltage AC side, and there's the lower voltage AC side. I've confirmed the value, it's 0.047 at 630 volts. I've hooked the scope on a divide by 10 probe. So over on our scope here, what we see is we're on 5 volts per division, which is 50 volts per division. And look at the size of that signal. I can't even get it into range on my scope. So it's, 50, 100, 150, 200, 250, 300. It's absolutely huge. And that is the HT transformer output. I think what I'm going to go ahead and do, just because it's really quick and easy to do, is to just dab another capacitor across this one here. As I say, I'll try 0.1, and we'll measure and monitor the DC bias voltage before and after adding that capacitor. So bear with me whilst I get set up for that. Right, let me explain the setup here. I have the digital voltmeter hung across the smoothing capacitor for the bias voltage. So this is measuring the maximum bias voltage this circuit can produce, and it's minus 31 volts, give or take. This is the capacitor of interest, and I've got a 0.1 at 650 volts here on a crock clip lead, and I'm just going to crock clip these leads across that capacitor. It'll be slightly out of your sight, and then we'll see what happens to the voltmeter. So here we go, one crock clip can go on there. I don't need to crock clip this on, I can just dab it on, and we'll see what happens. And aha! Houston, we have 80 volts of bias there. 82 and rising. That will fix this problem without any question. However, I think that's too much. I'd like to see about 50 volts there. So obviously our 0.1 is a little bit big. So let's see what else we can find. I think I've got a selection out just in case. What have we got here? Okay, I've got a 22 nanofarad at 630 volts there. So that's about a fifth of what we just put across. Remember, there's 47 nanofarads in circuit at the moment, so we're only going to be increasing this capacitor by 50%. So here's our 22 nanofarads about to be dabbed in similar fashion. We're looking for about 50 volts or so. That's on now. That's coming up nicely. Oh, this is perfect by the looks of it. 53, minus 53 volts. Right, well that will tame those output tubes beautifully. What I'm going to do now is to solder this in permanently across this capacitor, and then we can put the bias meters. Oh, actually we've got the bias meters over here. Why don't we, let's just have a quick look at one. They're still connected. So let's see what happens if I'll put that on top of that meter for the moment. Of course the HT is not on. So a bit of an experiment, this might not work. I would expect the tube current to go down way too low, because of course we have minus 50 volts now. So HT on, there's our 120 milliamps, on goes the capacitor, and down it comes. Fantastic, look at that. I tell you what, let's clip this capacitor on, and then we might be able to have a twiddle with this bias pot here, and see if we are able to bias the amplifier to a sensible level using this setup. Right, so here's the bias. Let's see what happens when we turn this up. This is coming up nicely. I don't know what it'll be. I'm looking for about 30 milliamps ish. Oh, look at this. This is perfect. I can change the bias from almost nothing. Look, 7 milliamps, all the way up to, well, we don't want to go up there, do we? And I can bias this perfectly at 35 milliamps or whatever. I will go and check the proper bias current, but it'd be around 35 milliamps. This is fantastic. So I think we've solved this problem. I will solder that capacitor in permanently, and then I'll come back to you with a figure for the correct bias current for 450 volts on the plate of an EL34. I thought you might be interested to see the online tool that I use to calculate the bias. It's a bias calculator on a site called Ted Weber. Here's the URL here, https tedweber.com bias.calc. It's a lovely little online tool. I use it all the time. You just select your class there, which is AB, push-pull. That's most of the amplifiers you'll ever see. You enter into here the tube type from a drop-down menu. In our case it's EL34. You enter in the plate voltage, 450, click calculate bias, and out comes the bias for this amp, 38.8 milliamps. I'll probably bias a little bit cooler than that at about 35 milliamps. And that's how you get your readings. Saves you getting the calculator out. Well, I just know some of you are dying to get your calculators out, so let me show you how you calculate it. Power is volts times amps. Volts times amps lights lamps is the old electrician's adage. Here is our voltage, 450 volts. Remember, it was 39 milliamps. We need that in amps, so it's 0.039 amps. Move the decimal point 3 places. 1, 2, 3, 39 milliamps. 450 times 0.039 is 17.5 watts. So that's what that tube will dissipate if we run it at that bias current of 39 milliamps. There are 25 watt tubes nominally, and 17.5 watts is 70% of 25 watts, and that's what they recommend you set the bias at, 70% of maximum tube dissipation. As I say, I'll set this a little bit cooler. I don't like things running flat out, so I'll set it about 35 milliamps. Right, well, armed with our figure for the bias current, we're now able to bias the amplifier. At the moment, as you can see, it's fairly low at 12 milliamps, so I'm going to turn this up. You'll notice the plate voltage coming down as we load the amp. It's a little bit higher actually than I calculated for 460. And another interesting thing I've just noticed is these aren't terribly well matched, these tubes. We've got 36 and 30. I think my next thing I'm going to do is just check these tubes on the valve tester. They have been rather roasted, and might just do a quick recalc for a 460 volt plate instead of a 450. So let's check those valves, get a new figure, and come back. So I went ahead and did the recalculation on the Ted Weber bias page, and for a 465 volt plate voltage it's 37 milliamps, not that much difference, so I'm going to go ahead and bias this at 35 milliamps. One of the customer's tubes was cooked, so we had to get rid of that. 3 are okay, but Paul wants a whole new set of tubes anyway, which he's going to fit and bias, so this is just ready for demonstration purposes. So there's the HT going on. We've got 460-ish volts, and as you can see there's a bit of a mismatch between the tubes, but they're not staying in, so it doesn't matter. So you can see we have quite a nice range on the bias adjustment, and I'll just set this right hand tube for 35 milliamps, and the left hand one is going to be a little bit, there's quite a big difference on that, 35, and the left one's 29, so there's like a 6 milliamp difference. Don't sweat a milliamp or 2 or 3 milliamps here or there on setting up bias. I would accept 4 or maybe even 5 milliamps difference. It's nice if they're completely matched, but that's really for the hi-fi nuts. A slight mismatch in tubes will give you, or even a big mismatch in tubes will give you richer harmonics and arguably a nicer sound. The only real negative about having a huge discrepancy is one pair of tubes will wear more quickly than the cooler pair. But anyway, that's perfectly okay, and I would actually let that go if the customer wanted to retain these tubes. Right, so there you go, a nice quick fix. Well, there you go, Paul. I hope you enjoyed watching that, and you've built a lovely amp there. There's nothing wrong with it. Good workmanship. The only problem was the design of the circuit. The capacitor value was too small, and I still don't like that method of deriving bias. Maybe it's okay, I don't know. I've never seen it before, and I don't like it. But we're back in business now with a nice range on the bias pot, and good luck fitting your new tubes and biasing up this amp, and enjoy playing it. And thank you all for watching. I'll see you all on the next video.